code permits parallel conductors within flexible codes provided specific conditions are satisfied. These conditions are firstly, that the conductors must be of the same type. Secondly, they must be of the same size. Thirdly, the conductors must be of the same length. Fourthly, they must be terminated in the same manner. And fifthly, they must be used in a single-phase circuit. Let's break down each of these conditions to ensure a clear understanding of their implications. Regarding the first condition, the requirement for conductors to be of the same type refers to the insulation material and the conductor material. For example, you cannot parallel a conductor with THHN insulation with a conductor with XHHW insulation. Similarly, you cannot parallel a copper conductor with an aluminum conductor. The code requires that the conductors have identical properties in terms of insulation and conductivity. Using dissimilar conductor types can lead to unequal current sharing due to differences in impedance, potentially overloading one of the conductors and creating a fire hazard. The second condition stipulates that the conductors must be of the same size. This refers to the American wire gauge, AUG, or KC male size of the conductor. For instance, you cannot parallel a 1/0 AWG conductor with a 2/0 AWG conductor. The current carrying capacity or ampacity of a conductor is directly related to its size. Using different sized conductors in parallel would result in unequal current distribution, with a larger conductor carrying a greater share of the load. This could overload the smaller conductor, leading to overheating and insulation failure. The third condition states that the conductors must be of the same length. This requirement is crucial for ensuring equal impedance across all parallel conductors. Even slight variations in length can introduce imbalances in impedance, causing unequal current sharing. Imagine two conductors, one slightly longer than the other. The longer conductor will have a higher impedance, which will impede current flow. This forces more current to flow through the shorter conductor, potentially exceeding its ampacity. To mitigate this risk, it is essential to cut all parallel conductors to the exact same length. The fourth condition mandates that the conductors must be terminated in the same manner. This refers to the type of termination used, the quality of the connection, and the tightness of the connection. Using different termination methods, such as crimped connections on one conductor and screw-down terminals on another, can introduce variations in connection resistance. Similarly, loose connections can create hotspots and increase resistance. These variations in termination resistance can disrupt current balance and potentially damage the conductors of the connected equipment. It is critical to use identical terminations applied with the correct tools and torque to the manufacturer's specifications to ensure a reliable and balanced connection. The fifth condition specifies that the parallel conductors must be used in a single-phase circuit. This limitation stems from the inherent characteristics of multi-phase systems. In a three-phase system, the current in each phase is inherently unbalanced due to the 120-degree phase shift between the phases. Paralleling conductors across different phases would create circulating currents, which would lead to increased losses and potential equipment damage. While paralleling conductors is generally permitted in single-phase circuits, it is crucial to carefully consider the specific requirements of the application and the equipment being powered. Induction heaters, for example, often draw nonlinear currents, which can exacerbate imbalances in parallel conductor systems. It is essential to consult with a qualified electrical engineer to ensure that the parallel conductor configuration is appropriate for the specific load. When implementing parallel conductors in flexible cords, several additional considerations come into play. Firstly, the flexible cord must be of an approved type, such as type G, and rated for the voltage and amperage of the circuit. Secondly, the flexible cord must be properly supported and protected from physical damage. Thirdly, the terminations must be suitable for use with flexible cords and must be installed in accordance with the manufacturer's instructions. The National Electrical Code (NEC) provides specific guidelines for the installation of flexible cords and cables. Article 400 of the NEC covers the use and construction of flexible cords and cables. Section 400.4 outlines the permitted uses of flexible cords and cables, while Section 400.5 lists the prohibited uses. Section 400.7 details the conditions under which flexible cords can be used for fixed wiring. It's important to consult these sections of the NEC to ensure compliance with applicable codes and standards. Article 310 of the NEC covers conductors for general wiring. Section 310.10 addresses the use of conductors in parallel. This section specifies the minimum conductor size for parallel applications, the requirements for conductor ampacity, and the methods for directing conductors in raceways or cables. It is important to note that the NEC requires that parallel conductors be sized no smaller than 1/0 AWG except under specific conditions outlined in the code. When using parallel conductors in flexible cords, it is essential to ensure that the ampacity of the combined conductors is sufficient to carry the load current. The ampacity of a conductor is the maximum current that it can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by its size, insulation type, and ambient temperature. The NEC provides ampacity tables in Article 310. These tables list the ampacities of various conductors under different conditions. When using parallel conductors, the ampacity of each conductor must be derivated to account for the increased heat generated by the multiple conductors in close proximity. The NEC provides derating factors in Article 310.15. These derating factors are based on the number of conductors in a raceway or cable. It is also important to consider the voltage drop in the parallel conductors. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in a branch circuit not exceed 3%. To calculate the voltage drop in a conductor, you can use Ohm's law, which states that voltage drop is equal to current multiplied by resistance. The resistance of a conductor is determined by its length, size, and material. The NEC provides tables of conductor resistance in Chapter 9. In summary, the code allows parallel conductors to be run via flexible cords if certain conditions are met. These conditions include that the conductors are of the same type and size, the conductors are of the same length, the conductors are terminated in the same manner, and the conductors are used in a single-phase circuit. It is also important to consider the ampacity, derating, and voltage drop of the parallel conductors. By following these guidelines, you can ensure that the parallel conductor installation is safe, reliable, and compliant with applicable codes and standards. Remember that electrical work can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns. Now, let's apply these principles to the specific scenario described involving a 460 volts 208 amp single-phase induction heater connected to a control panel using a 1/0 4-wire Type G flexible cord with 2 conductors in parallel for the hot leg and 2 conductors in parallel for the neutral leg. First, verify that the Type G flexible cord is rated for 600 volts, which is sufficient for the 460 volts application. Second, confirm that the 1/0 AWG conductors are of the same type. For example, all conductors should have THHN insulation or all should have XHHW insulation. Mixing insulation types is not permitted. Third, ensure that the length of each 1/0 AWG conductor is identical. Precise measurement and cutting are essential. Fourth, inspect the terminations at both the control panel and the induction heater. Are the connectors of the same type, properly crimped, and torqued to the specified values? Fifth, in this application, the induction heater operates on a single-phase circuit, satisfying this requirement for paralleling. Next, check the ampacity of a single 1/0 AWG conductor. Referring to NEC Table 310.15, a 1/0 AWG copper conductor with THHN insulation, operating in an ambient temperature of 30 degrees Celsius, has an ampacity of 150 amps. Since 2 1/0 AWG conductors are used in parallel for each leg, the combined ampacity would initially appear to be 300 amps. However, derating factors must be applied. According to NEC Table 310.15, If there are 4 current-carrying conductors in a raceway or cable, a dirting factor of 80% must be applied. Therefore, the adjusted capacity is 300 amps multiplied by 0.8, resulting in 240 amps. This 240 amps is sufficient for the 208 amps load of the induction heater. Finally, evaluate the voltage drop. Using a voltage drop calculator or the formulas provided in NEC Chapter 9, calculate the expected voltage drop for the length of the flexible cord. If the voltage drop exceeds 3% of the supply voltage, consider using larger conductors or shortening the length of the flexible cord. By carefully considering all of these factors, one can determine whether the proposed parallel conductor configuration is compliant with the NEC and suitable for the application. If any doubts or concerns arise, it is always recommended to consult with the qualified electrical engineer to ensure safety and code compliance. Remember, safety is paramount when working with electricity. Always de-energize circuits before working on them and follow all applicable safety procedures.